Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 10th, 2026, just 3 days ago. It demonstrates that the failure of standard diffusion models to learn from pre-trained representations is fundamentally a geometric problem. And by fixing this, the authors enable a standard 131 million parameter model to achieve an FID of 3.37, where prior methods completely failed to converge. The paper is titled Learning on the Manifold, Unlocking Standard Diffusion Transformers with Representation Encoders. And, as we'll see later, the results are really impressive, proving that we don't need computationally expensive width scaling to get high-fidelity results. And for those interested in the implementation, the authors have shared their code on GitHub. To visualize that performance gap, Figure 1 plots the FID scores on ImageNet, where lower values indicate better image quality over 200 training epochs. Notice the blue lines at the top, representing standard flow matching with Dyno v2 features. They effectively flatline around 20, failing to converge because the model fights against the geometric mismatch. However, the red line at the bottom highlights the proposed method, RJF. By respecting the manifold geometry, it quickly descends to an FID of roughly 5, significantly outperforming even the standard versus AE-based baseline shown in gray. To understand the root cause of that failure, Figure 2 visualizes the latent space as a hypersphere. Standard Euclidean flow matching connects points with straight lines, like the dashed orange path, which acts as a cord cutting through the sphere's empty interior. This forces the model to learn in undefined regions where no real data exists. Even the dashed purple path, which targets projected noise, still cuts through this void. Instead, the method uses the solid blue curve, the geodesic, to stay strictly on the surface, ensuring the velocity fields remain valid. Well, Figure 3 quantifies this geometry gap by comparing the radial norms of the latent features. The blue distribution represents the standard Gaussian prior, which forms a diffuse shell where probability mass spreads across a range of values. In contrast, the orange spike shows the Dyno v2 features. Because of layer normalization, these features are rigidly constrained to a single radius, creating a hard shell with almost zero variance, which forces the model to bridge incompatible geometries. So, Figure 4 investigates whether wider models are essentially required to solve this. The top row tracks training loss with the standard Euclidean objective. On the left, narrower models fail to minimize the blue angular loss because they get stuck fighting the orange radial error. However, the bottom row reveals the truth. When the authors mask out that radial component, even the smallest model on the far left converges perfectly, which proves that the bottleneck is geometric interference rather than model capacity. Alright, following up on that geometric proof, Table 1 details the actual generation performance on ImageNet. The results for the smallest model in the top section are particularly striking. While standard Euclidean flow matching, labeled EFM, effectively breaks down with a poor score of roughly 24, the proposed RJF method drops this to 6.77. This confirms that even compact models can work well if they respect the manifold geometry. Moving to the extra-large models at the bottom, RJF continues to lead, achieving the best overall FID of 3.62. Well, Table 3 breaks down exactly which geometric fixes drive those gains through an ablation study. The first two rows show that simply projecting the noise onto the sphere, labeled plus SN, provides only marginal improvement to roughly 22 because the interpolated path still cuts through the manifold interior. The massive jump appears in the third row, where Riemannian flow matching properly curves the trajectory, slashing the FID to 7.06. Finally, adding Jacobi regularization and extended training at the bottom polishes the score to an impressive 3.37. So, Table 2 benchmarks the full model against state-of-the-art approaches on ImageNet. The upper sections list standard pixel and latent diffusion models, which typically require hundreds or even thousands of epochs to converge. However, looking at the efficient 80-epoch regime at the bottom, the proposed RJF method stands out. It achieves a class-conditional FID of 3.62 without guidance, distinctly outperforming the Euclidean baseline of 4.28. The highlighted precision and inception scores further confirm that correcting the geometry drastically improves semantic fidelity. Wrapping up, two takeaways stand out. First, the bottleneck in diffusing representation latents is geometric, not architectural. Second, by fixing this with Riemannian flow matching, we can use standard, efficient models to generate high-fidelity images, avoiding the need for expensive width scaling. This effectively unlocks the rich semantic space of pre-trained encoders for generative tasks. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.